anyway that is good for you, I have no problem. Okay. Okay, right. Now let's come here. Right. Now what we have here is the Frost diagram. This is another diagrammatic representation of the potential data or redox data. Right. This is basically, as I mentioned in the previous class, Arthur A. Frost. He is the one made this plot. Again, to make the life easy, right? Instead of going redox table after table, simply take one species, plot all the possible oxidation state, and derive the chemistry from a single plot. That's the whole idea. So what it talks about here, as I have already drawn here, this is a graphical illustration of the stability of the different oxidation state of an element. Keep in mind, the relative to its elemental state, that is zero oxidation state. Say, for example, I have a I have a 5, M4 plus, M3 plus, say for example +1 and M0. Maybe you will have a M-1, M-2. All these you may have. Now, this diagram, what it represents, it is a plot of Ne0, that is a capital N, that is the oxidation state, that's oxidation number, multiplied by the reduction potential against the oxidation state. Okay. One thing you need to remember, this is as I underline, relative to its elemental form. This is not like your Latimer diagram where we dealt with M5 plus to M4 plus, you have a, say for example 0.51 volt. This is the potential. Again, who is this? Jashwant Kumar. Jashwant Kumar, I will remove you. I don't need any reaction from you. Chukka Jashwant Kumar, right? If you do it again, right, I may report to the competent authority, right? It distract my class. Okay. I hope you understand. Right. Let's cover. Right. I mean, listen to me. Listen to me. What we have here is that, as I mentioned, in the Latimer diagram, what we do is that M5 plus to your M4 plus. Here you have a 0.5 volt, say for example. This potential, we looked into that and see all the potential for the redox couple present in the Latimer diagram. We talked only about the individual potential. Here what it talks about is that the potential that is plotted here is that the oxide, say for example M5 plus is not M5 plus or 4 plus, but with respect to your M0, right? I will show you the Latimer diagram and how we do that. That I will explain after a couple of slides. So I hope you, first of all, you need to understand that this is basically the potential that is plotted is not an individual redox couple. This is the potential with respect to the elemental form or the zero oxidation state. Okay, I hope you got it. Now you will be able to understand further. Right, again I have graphically illustrated. There is a delay is there. Yeah, now you can see here a graphical illustration of the stability of different oxidation state relative to its elemental form. And note here Ne0, it were very close, similar to what we say that, right, the delta G equal to minus NFE0, delta G0 equal to minus NFE0 is similar to the standard equation that you study in electrochemistry during your JEE preparation or in the class 12. But here what we have, a capital N, basically an oxidation state, right, that you keep in mind, which is multiplied by my reduction potential. What is the reduction potential? I have shown here, right? The bottom that I have shown, Xn plus N electron because my oxidation state is capital N, N electron gives you X0. This is the potential that I am plotting after multiplying with the oxidation state. Okay. So capital N E0 is proportional to the free energy of a compound in oxidation state of N. Keep in mind, this is relative to the elemental form, not anything else, not between an individual couple. It is relative to the elemental form. Okay. Now again, I repeated the same thing. I repeated here. Ne. So that is the bottom. You see, capital N E0 equal to minus G0 divided by F. Right. That is the relation that we have at the end of the day. So what you need to remember, here we plot the oxidation state multiplied by the reduction potential. What is the reduction potential? The reduction potential with respect to the elemental form. Okay. Now you come here. This slide comprises everything, all the Frost diagram, what and all we need to read, what and all we need to study. This diagram, this slide tells you completely about the entire Frost diagram. I sum up everything together. Right. Number one we'll see. What we have here is that basically what I have plotted N, capital N E0 versus oxidation number. So the species that is lying at the bottom, right, the lowest N E0 value, which in turn what we have is that highly stable species in terms of your thermodynamics. Right. Again, I am not going to talk about the number of electrons here. I'm talking about the oxidation state multiplied by the reduction potential. In both sides, you have a reduction potential, but here what we say is that not a small n, capital N. The most stable oxidation state comes here, right? The stable oxidation state. So further we can understand from this diagram what and all this species, say for example the mark species, the chemistry of this species we can study. I will give some examples later on. Okay, that's number one. That is from top to bottom, what is happening? The stability of the oxidation state increases. Okay, you don't need to bother about anything. Simply look at the diagram, a standard diagram for nitrogen, Frost diagram. If you look at that one, you can simply say that the species that is lying at the bottom is the stable oxidation state. Right. Number two, what we have is that, yeah, from the slope, it's obvious, right? From the slope, you will be able to find out the standard reduction potential, whether it's a high reduction potential or low reduction potential. From the slope, you will be able to find out. Now you have a low standard potential, there is nothing but a reduction potential. Here you have your standard high reduction potential. From this, you can deduce the property with respect to some other couples, right? Say, for example, I consider this couple and this couple. I can look at the slope, right? Whether it's a negative slope or positive slope, whether it's the slope is high slope or low slope. From there, I will be able to deduce the property. Again, at the end of the day, you know what is playing the reduction potential. We play with the different diagram for our convenience, make a representation to read it quickly and understand, right? Number three, what I have, third plot what I have, look at the species at the bottom. Say, for example, this one diagram, right, or this one. And this one you compare, the top one what we have. If you compare this, the top one and this one, what we have there, this species, that the species liable to undergo reduction. Okay, what does it mean if it is reduction means what? Can anyone unmute your microphone and tell me?
Gain of electrons.
Oxidizing
Gain of electrons.
and oxidize water.
Right, yes. Okay. Now, at the same time, what is the property? This species is liable to undergo oxidation, or this species or this species. What does it mean? Can anybody tell?
So this is an oxidizing agent
Which is?
that is liable to undergo reduction.
This one, the bottom one? Should be a
reducing agent.
yeah, right, right. So you will be able to see from relative to, right? You cannot make it as a universal concept, right? Within the diagram, considering the species, all the species given in the diagram, you can simply predict, yeah, this is liable to undergo reduction. That means it is highly oxidizing. At the bottom, what I have, it is liable to undergo oxidation. That means it is highly reducing. Okay. Now, the fourth one is very straightforward. You will get your E0 value if you take the slope of this, the particular, the line that joining two different species. Right, this is one species, this is another species. If you take the slope, what I will get is that it looks very simple, but when you have the same element, you have a multiple oxidation state. When you have it in a simple diagram, this is much helpful instead of going and reading the redox table. Right, simply take the slope, you will be able to find out your E0 value of the redox couple, that is the two species that is involved in the redox reaction. That is the fourth one. Fifth one. Fifth one, what we have? Right, I have already mentioned here, right? Unstable with respect to disproportionation reaction. That's what we have seen here in the disproportionation reaction we have seen in the Latimer diagram. Now, how do I find out? Say, for example, typically look at this. Right, here is one point. This is another point. This is another point. This is another point. Point means what? Four different oxidation states. Now, if I connect these the oxidation state, and the species that is lying above the line, in principle, will undergo disproportionation reaction. I don't need to calculate, I don't need to see the potential, nothing I need to do that. Looking at the three species, the two species, if you connect here with the line, then the species that is lying above the line is liable to undergo or unstable with respect to disproportionation reaction. Right? I will give you examples, then you will be able to understand what I mean is that it's simply mug it up. No, it's not that. This thermodynamically we can prove as we have done in the Latimer diagram. Now, number six, what we have, just opposite reaction. Suppose if I join the line of this the species and this species, and the species lying at the bottom below the line, below the straight line connecting these two oxidation state. Right now we see that now the species 1 and species 2 can undergo a comproportionation reaction. Right, I hope you are following. Right, in the previous case, the disproportionation, that is the species that is lying above the line undergo disproportionation reaction. In the sixth case, the sixth plot, what we have is that the species 1 and 2, when I am connecting it, if there is a species that is below the line, that means what it implies is that yeah, the species 1 and 2 can undergo comproportionation reaction. I hope you are following. Now, let us take the typical nitrogen Latimer diagram. We'll take a nitrogen Latimer diagram. Yesterday, I have shown that. This is an acidic pH. Acidic pH. I have already given the potential. I marked the oxidation state A, B, C, D, E, F, G, H for convenience. Like usually we used to write on the blackboard and explain, but now it's online class. Now everything is I put it here. Now the +5 oxidation state, +4, +3, and so on. Now, what I need to do is that, as I said, when we look at the Frost diagram, let me draw here. So here I have a Ne0, and here I have an oxidation state. Okay, this is right. The stability increases, or the species that lies here is the highly stable species. Now the Ne0, basically what do I get? Is not the simple potential of NO3 minus 2 N2O4. It is the potential of NO3 minus 2 N2. Okay, this is the potential that I am talking about. Okay, same is the case N2O4 to N2. HNO2 to N2, right? NO2 is a, right. So how do we find it out? Right, yesterday I mentioned that how do we find out the reduction potential of non-adjacent oxidation state or non-adjacent species. So you have the potential, right? NO3 minus to N2O4 available, N2O4 to HNO2 is available, and so on. Now, what I can calculate using the relationship that I have shown in the previous class, you can calculate the potential corresponding to the reduction of NO3 minus to N2, that is oxidation state is 0. Okay, the same way for each and every species with respect to the elemental state, you need to calculate up to here. Then if you have a negative oxidation state, what should be done? That is from N2 to NH3OH plus N2 to N2H5 plus N2 to NH4 plus. Okay, so you will have A2H series of potential that you have calculated. Please again don't confuse. This is not the potential that we are talking about the couple of NO3 minus and N2O4 or N2O4 and HNO2. This is the potential with respect to the elemental state, right? Okay, I have already calculated. I put it here. This is the relationship that we use, right? We'll talk in terms of a delta G, and then you go here E equal to N single prime, and then you add up here and you find out. So I have calculated for A2H, I have calculated all the potential I have calculated, right? Once I calculated the potential using this relationship, now my next job is multiply with your oxidation state and make the plot. Here I have a N, here I have a N E0. That's all, that's done. Then we need to read the diagram that we have drawn using this potential data, right? I hope you follow. Yeah, again, this is, simply I have put in multiplied it, and then how I am going to plot it. There's no need to read it away. Now look at here. This is an acidic solution of that nitrogen frost diagram in acidic solution. So you will be able to see here the all possible oxidation state in a single diagram, all possible nitrogen species and their chemistry can be understood from the simple diagram, right? Now you have your NH4 plus here and then N2H5, nitrogen and so on. Now what we have here is that the HNO3 occupies the top corner, right? So you will be able to understand now based on what I already explained for the Latimer diagram, the general description. Now one can easily tell, looking at this diagram, HNO3 is supposed to be a powerful, anybody?
Oxidizing agent.
Oxidizing agent, right? So we'll be able to read it, right? So again, so overall looking at this one, I'm not comparing with anything else, right? Simply looking at the entire diagram, the species that is lying at the top corner, right corner, top right corner, is considered to be the powerful oxidizing agent, right? Now here, this is the basic solution, right? As I said, your potential changes when the pH changes. Here for the same nitrogen, your basic solution, the potential data changes. In the Latimer diagram, the entire diagram changes. Entire diagram changes. Now you will be able to see the NO3 minus is no more a powerful oxidizing agent, right? I hope you got it. In the previous case, what we have seen, HNO3 that occupies the top corner, right corner. But now in the basic solution, this is not the case. So the solution pH significantly influence the property of the species concerned. That we know that your potential changes as a result of oxidizing or reducing property changes, right? Now, one thing is clear, right? You have your nitrogen always at the bottom, right? So consider to be the stable, the oxidation state, we have your zero oxidation state. And we'll read a little more further on. Now look at it. Okay. Now look at this diagram. So I'm again taking the general diagram. and then reading it again and again, right, to make you understand, right? I already have given you the general description, general characteristic features of a Frost diagram. Now I have taken an example. I am explaining one by one. Now, in acidic solution, that you keep in mind, acidic, that is very important. That pH is more important. In acidic solution, the most stable oxidation state or the most stable species of nitrogen is NH4 plus. Okay. Now, if I go here in the alkaline pH, in the basic solution, that is not the case. Who is the stable oxidation, the stable species?
N2, sir.
N2. N2 is the stable species. Okay. Right. I hope you are getting. I mean, the lowest lying species corresponds to the most stable oxidation state of the elements. Okay. Nothing much to read here. Yeah, this slide is very simple. I have already explained. This we are calculating the slope, and then what we get is the E0 value. Right. Don't we know the E0 value for this redox couple? Yeah, you know. But when you have a multiple oxidation state and put in a single diagram, you can quickly look at the slope and then you can find out the E0 value, and then you will be able to predict the property in overall. Okay. Right. Again, I took the one example. What I have taken is the couple that I have marked here is the HNO2 to NO couple, right? This is the couple that I have taken. Okay, you can see that. So what I do is that, again, is a repetition. Yeah, find out the Ne0 value, find out the oxidation state, and then find out the slope, what is the E0, and it turns out to be 1 volt. Right. So I will be able to predict the property by looking at the slope, which in turn, right, the E0 value, and then I predict the property of the particular redox couple. Okay. You will understand why did I do here, right? You will be able to see that the couple of slides, right? Oxidizing or reducing. Already I have mentioned that is in the previous earlier diagram. Earlier diagram, what I have mentioned, right? This species, the HNO3 is oxidizing. Okay, if you look at this one, it is a powerful oxidizing agent. It occupies the top right corner. On the other hand, the species that is lying at the bottom, right, lying at the lower region of the Frost diagram, should be a powerful reducing agent. In principle, experimentally, it may or may not go. Right, there are many complications may be there. But theoretically, in principle, based on the redox data, if the species that is lying on the top corner is a powerful oxidizing agent, it implies that the species that is lying at the bottom, that is a lower region of the Frost diagram, is supposed to be a powerful reducing agent. I will give you an example. Maybe we'll go further, you will be able to understand. Oxidizing agent coupled with more positive slope, I think you know very well, and the reducing agent coupled with less positive slope. If the line has negative slope, I mean higher lying species, a reducing agent. And if the line has a positive slope, the higher lying species is basically an oxidizing agent. Don't get confused. Basically, what we play is that we're simply playing with the E0 value. Right? In a different way, I represent, I interpret for my convenience to quickly read out, to quickly understand the chemistry of that particular species. Okay, look at here. What I have given is, right, HNO3, nitric acid, and the NO, right, nitric oxide. Now, if I look at the potential with respect to, again, I repeat, with respect to the elemental state, it may or may not be true experimentally. With respect to the elemental state, who has the, simply looking at this one, equation O3 is plus 6.2, that is Ne0. And here what we have the plus 3.4. Okay. Now, from the coordinates, right, you find out the potential. Right? Why I marked here? Just to know whether identifying a strong or weak agent. right? Strongly oxidizing or weakly oxidizing, and vice versa. Now look at here what we have. I read from the plot. I have translated here from the coordinates of HNO3. Yeah, 5, that is oxidation state. 6.2 is the Ne0. And NO, that is nitric oxide, the +2, that is oxidation state. And 3.4 is the Ne0. Now, if you write the half reaction that we have here is that now HNO3 2N2. Don't make mistake here. Every semester I used to face this problem. Sir, how do you say? I am talking about the reduction potential with respect to the elemental state, not to the adjacent species, right? I hope I'm not talking about these two couples. I am talking about the HNO3 and nitrogen, right? There should not be any confusion here, right? Now what we have is a HNO3, yeah, 10 electron goes here. My E0 is 1.24 volts. On the other hand, now you may surprise, right? Nitric oxide, 4 electron, and then you go to nitrogen, you get a 1.70. What it implies? Anybody? What it implies?
Sir, NO is more powerful oxidizing agent.
Right. What do we have? Yeah. Sometimes back only I said that HNO3 is a powerful oxidizing agent. Now I'm telling that, yeah, you see here, right? NO is more oxidizing with respect to HNO3. Again, in terms of, please understand. Again, don't confuse. Don't confuse in terms of the reduction potential with respect to elemental state. In experimental condition, it may or may not, sorry, NO may or may not be converted to N2, right? What we are talking about here is my plot talks about the potential with respect to the nitrogen. So I'm talking in terms of the reduction potential with respect to the elemental form. Okay, I hope you are following, right? Right. Experimentally, lot of complications will come, right? So we will go a little later on. I will give you some of the problems. You will be able to understand that's what actually I mean there, right? Find out the property. I have already, it's 1.24, right? This is 1.7. So the E0 value is, more in the case of NO to N2, right? If you go here, right, what I'm talking, look at this diagram. Look at this diagram. Don't read other part. Only the red color line you see. What I'm talking about, HNO3 to N2 and NO to N2. When I look at this elemental, with respect to the elemental oxidation state, among these two, what are these two? HNO3 and NO. Yeah, NO is a powerful oxidizing agent based on the reduction potential that we have, right? That's what I have. Now look at it, right? I have already explained the higher reduction potential, that is this couple is a higher reduction potential, and this will be the lower reduction potential, right? You can read it from the, you can read it that basically.
Excuse me, sir.
Hmm.
Sir, how reduction potential from NO to N2 is coming bigger? Because on the diagram, HNO3 has more reduction potential than NO.
You
So
calculate that potential, I have already shown, right? HNO3 to N2, right? What you have here is that I have already given 6.2, here it is there, and then you have the oxidation state is +5. A simple mathematics. Don't get confused. Let me explain you. This is this kind of question every semester I used to get. As soon as look at the time, I'm sorry, how it is possible, right? HNO3, how it will be possible? It's that, not the powerful oxidizing agent. The potential is less. No, it is not the case. Look at very carefully, patiently. Don't be in hurry. At the end, you ask, right? If there is any doubt, I will explain it. There is no ambiguity. There is no problem. There is no error here, right? Okay. Now look at here, right? The higher reduction potential and lower reduction potential, and already I have explained. Species liable undergo reduction. That is the species that's already the oxidizing agent. Again, the same thing I am repeating again and again, right? I think I should not repeat. right? I hope you follow the same diagram. I have given an example here, right? HNO3 looking overall. I'm not comparing anything. Looking at the entire diagram, yeah, find out who is occupying the top. In the previous slide, what did I do? I compared the HNO3 with the NO. I did not do anything else, right? Now, overall, I look at this one. Now, this species HNO3, which is liable to undergo reduction. On the other hand, the species that is lying at the bottom, right, which is liable to undergo oxidation. Okay. Now, right, again, the same diagram that I have shown, the disproportionation reaction, the disproportionation reaction. That's M plus undergo reduction and on oxidation. Now, what we said in yesterday class, what we say, whenever the left hand side potential is less with respect to the right hand side potential, the species that is lying in the middle will undergo disproportionation reaction. A pink color box that I have shown. Number 1, number 2, number 3. Now we will look at that. What I stated, that is true. That is NH2OH and NO and N2O4 will undergo. Yes.
Sir, which species we have to take on the right side? Reduced one
No, I did not get your question.
or oxidized one?
No, I did not get your question.
Sir, which species, we have to take on the right side?
See here, I think yesterday you did not follow properly. What the Latimer diagram, what it says, M5 plus, that is extreme at my left hand side. I go M4 plus, I go M3 plus, I go M2 plus, and again I go M plus 1, and I go M0. I stop here, right? This is the sequence. There is no ambiguity, there is no change at all. There is nothing, it's a reduction potential. M plus 5 to 4 plus, 4 plus to 3 plus, 3 plus to 2 plus, 2 plus to 1 plus, and so on. Now, I look at here, say for example, here is minus 0.5, here is plus 0.7. So,
sir, in the above example, you took M plus 2, M2 plus on right side.
right side.
In example, M plus 2, M2 plus, and in the backward side.
You mean this diagram?
Yes, sir.
No, I think you're confusing, right? I am talking about the Latimer diagram. This is what I have shown here is you are completely confusing.
Sir, I am talking about disproportionation, sir. Which species we have to take on the right side?
Yeah, please listen. I understand you're confusing, right? Now, you don't look at this one. This is, I have separated the schematic representation. Now, this is not the Latimer diagram. What I have marked is not a Latimer diagram. On the other hand, what I have given at the bottom is a Latimer diagram. Are you clear now?
Yes, sir, but I am asking that which species we have to take on the right side in disproportionation reaction, reduced one or oxidized one?
My goodness. You look at here, M5 plus, there is no which direction. There is only one direction, plus 5 to M0. Okay. Now you look say for example, I'm not able to get what he's asking about, right? Say for example, I take this species here. I have started from M5 plus, 4 plus, 3 plus, 2 plus, 1 plus. There is a one direction goes here. Now look at the Latimer diagram. See that your right hand side potential, say for example M4 plus to M3 plus, right, which is higher than my left hand side potential, which is M5 plus to 4 plus. So what it implies, M4 plus will undergo disproportionation reaction. Say for example another one goes here. Say if I have a plus 5, here I have a plus 7. Okay. Now, this is I'm talking about the M2 plus, M plus 1, M plus 3. Here, when I talk about the M3 to M2 plus and then to M plus 1, now M2 plus cannot undergo disproportionation reaction because the left hand side potential is low with respect to the right hand side potential is low with respect to left hand side potential. Are you clear now?
Yes, sir.
Right. Right. Now look at, you have your number 1 species, number 2 species, number 3 species. That's NH2OH, NO, N2O4. Right? 3 species. Now we'll go here. Right. This diagram I have already shown. Again, I'm not going to explain. This is that the same potential data I represent in a different way. I will be able to get it here. Now look at here. Look at here. This is both acidic as well as this is acidic. This is basic. Okay. Now pick up the species. Already it is marked. Right. Pick up the species. What are the species will undergo disproportionation reaction? Unmute your microphone and tell me. Look at the alkaline pH, the blue color one. Blue color one. Come on. I hope you are listening.
Sir, NH2OH.
H2OH, NO, and 2O4.
NO and N2O4.
Right. In the case of your acidic solution, you have your NH3OH plus. Okay. So within the pH, change in the pH, you will be able to see that how much the chemistry changes. I am able to read it in a single diagram, both alkaline as well as acidic in a single diagram. So I don't need to see the reduction potential in a different table. In a single plot, I will be able to see that. Okay. Yesterday we have seen the hydrogen peroxide, H2O2, that gives your H2O plus oxygen. Right. Again, the basic solution as well as in the acidic solution, how this disproportionation reaction takes place. That is basically I join this line. Obviously, your H2O2 is lying above the line, and then what we have is that it is susceptible for your disproportionation reaction. I hope you are following. Right. Now what we have, the comproportionation reaction. Right. This I have already explained. Right. Again, I'm not going to explain. No, look at here. Not many species will be there. Say, for example, say NO and N2O4 in basic solution. What can these two species can react together and produce your NO2 minus. The same is the case here. You have a species, right, which can undergo a comproportionation reaction. Right.
Excuse me, sir. I have a doubt in the previous.
Yeah.
Sir,
Yeah.
N2O, N2 and NO, all of them lie on the same line, means
N2O and
N2 and NO.
N2 and NO. No, not really. A small change is there, right? This is a, I mean, the diagram that you are not able to say. You want to say that N2, sorry, you want to say that N2, N2O and NO. All these are on the same line. That's
Yes,
what you want to say?
that is my doubt. That is my doubt.
No, it is not that. Yet there is small change in the slope is there, right? It's not a simple, perfect straight line, right? Because if you see the potential already, that in the earlier what I have shown in the potential, when I have shown you the calculated the E0 with the NE0, the E0 and NE0, the potential is not the same, right? It looks like a straight line, but it is not the straight line. You will be able to see, look at the, you will be able to see the difference. I'm not sure. Let me zoom it a little bit. You will be able to see. I hope, right? Look at the straight line between N2 and NH2OH, the blue line, and N2 and NO, right? You will be able to see some difference in the slope. It's not that perfect straight line as in the case of N2 to NH2OH. There is a very small difference in the potential. It is there.
Sir, in that case, why did we not mark N2O for either of comproportionation or disproportionation?
Which one?
Sir, if this is not on a straight line, then we did not mark N2O for either of, means we did not mark in comproportionation and we did not mark in disproportionation as well.
No, your question is different. Which couple you are talking about? N2O4?
N2, N2O and NO. These three species.
Yeah. I got it. You see, no. You are telling that Say for example, let me pull out the page. Your doubt is that I have a N2 and N2O and NO. Say for example, this species, say this one here, if there is a, say for example, it is here, it is here. Yeah, this is what you're asking about, right?
Means, yes, we should
Either
have
this one
marked
or
it
the
in.
other way around. Other way around
Yes,
also possible, na? Right?
yes,
If say
sir.
for example N2O is little lower, yeah, this will not. Yeah, it is possible. If you, I'm not marking, I'm showing only the diagram which is visibly seen. That if you calculate the potential, if you look at the slope, you will be able to predict whether this species will undergo the disproportionation or comproportionation reaction will takes place or not. It is possible. Here, what I want to see so is that visibly, apparently, as soon as you look at this diagram, which is lying below that even as joined the line, this is, I mean, well below the straight line. That means this is, these two species can readily undergo comproportionation reaction. When you look at here, the same thing, what you are telling that, say for example, this N2O is somewhere here. Let me draw here. Let me draw here. There is a difference in the slope, right? N2, that is here, and let's say for example NO is here, that is, these two are in perfect straight line. Then let's put the dot line. This is somewhere little lower. That who is that? N2O. Right, now what can be done? Right, we can put it here. This species can undergo this comproportionation reaction if this much difference is there. Definitely, there is no doubt. But when I compare with this one, NO N2O4 and NO N2, the more feasible reaction will be, more facile reaction will be N1 N2O4 rather than N1 N2, simply because of the reduction potential. I hope you are getting it.
Yes, sir.
Right. Okay.
And sir, can you explain the mathematics behind doing this trick that if it is above the line, then it will disproportionate, and if it is below the
So
line?
there is no trick here. There is no trick here. This is the Arthur Frost has developed here. What is the mathematics? Well, simple. You find out the potential for NO to NO. Sorry, we look at the reaction. NO is getting, I mean, reacts with the N2O4 and producing your NO2 minus. Now, what we need to do, find out to prove. That's what we call the. Looks like a magic or a trick. It's nothing but a finding out your delta G value. Right? He put forward this diagram based on his research work. All this he has done, put in a nice way. At the end of the day, bottom line is what? Your E0 or delta G, nothing else. I hope you are getting. The credit goes to Arthur Frost because he formulated this diagram. Yes.
Okay, sir.
Sir, I think according to slope, it is determined that it will go disproportionation
Yes,
or
yes, yeah, yeah. Slope, when you are taking a slope, what you get a E0 value. Right, when you get a E0 value, if you want to find it out, you get your delta G. So at the end of the day, for bottom line is what? E0, which in turn delta G0. He is clever enough, Arthur Frost is clever enough, put it properly so that I will be able to read. I don't need to do any calculation. That's what, as simple as. Right. Okay, now the question that he has asked, that whether it is a comproportion reaction goes or not. Yeah, you can balance this reaction then and find out, yeah, NO, N2O4, NO2, that gives your balance. Then you look at the potential, you will be, this will be a feasible, favorable reaction with delta G negative or positive E0 value, right? Right. I'm not bothering about the balancing, but because you are well familiar with the balancing. Right. Now we come to little complex diagram. Right. Little complex diagram. Right. What I've taken is that manganese. Manganese. We'll take a 5 minutes break.
yes, sir.
5 minutes break. Yes, sir. Okay, let's continue. Yeah, what I have shown here is the another the Latimer diagram of manganese. Right, you have a interesting chemistry is that you have your multiple oxidation state. +7 goes up to 0. Of course, we don't have any of negative. That's quite straightforward without any confusion in making the Frost diagram. So acidic solution and basic solution, right? I'm not going to read all this data, right? I mean, so what we need to understand here is the potentials are given from this. Here, what the purpose of showing these two diagrams is to make the Frost diagram. Okay, so because it's online, you will not be asked to make the Frost diagram from the Latimer diagram because it's a online drawing is difficult. So you will be asked the indirect questions that is related to your the chemistry of a particular species. Now look at here. What we have this is an acidic. The blue one is acidic. This is your acidic, and this is your basic. Right. Now let me ask a question. Right. Couple of you unmute your microphone and read the Frost diagram. First, let us look at the acidic. Acidic, what are the properties? So far, I have explained all the properties, the characteristic features of a Frost diagram. Now you unmute and then tell one by one, right? What are the property that you can read from this diagram in the acidic solution? Quick.
MnO4 minus is powerful oxidizing agent.
Okay, number one. Then
Mn2 plus is strongest reducing agent.
strongest reducing agent. Okay.
HMnO4
Mn
minus
and Mn.
go on reaction.
Okay. Anything else? Look at the pink color line, the basic solution, and then compare these two lines. What is the difference in the acidic? Yeah.
Mn2 is
Pardon?
So Mn is powerful reducing agent.
Okay. Mn is powerful reducing agent. Abhay Kumar, you said something. Sony.
Mn+3 undergoes disproportionation.
Mn3 plus undergo disproportionation reaction to Mn O2 and Mn2 plus. Okay. Yeah, he's talking about this one. Look at carefully, right? Look at carefully, right? Yeah. And then
So in basic medium, so MnO2 is going to come proportionation reaction.
MnO2 is going to come
Means
proportionation.
Mn2O3 and MnO4 3 minus goes to
Yeah,
Mn.
it goes here. Okay. Right. So in basic solution, Mn2 plus doesn't exist, right? It exists in the form of MnOH twice. Okay, this is a free form. In acidic solution, Mn2 plus. When you do, those who have done the redox titration, right? MnO4 minus, right? MnO4 minus, MnO4 minus. Yeah, you will get your Mn2 plus in the with the oxalic acid, right? I hope you can remember oxalic acid, the redox titration, or Fe3 plus, right? The redox titration. In acidic solution, Mn2 plus is the most stable species. On the other hand, in the basic solution, what we have Mn2 plus doesn't exist. Mn2 plus instead of that MnOH, OH twice, manganese hydroxide. Okay, right. I have put in a different way, right? Your MnO4 minus, HMnO4 minus, MnO2, and Mn2 plus, and then Mn is somewhere here. And then I have enlarged that, right? What we have MnO2, HMnO4 minus, MnO4 minus. This is the describe which reaction it describes? Disproportionation reaction. I'm hearing from the same students, right? Others also should respond, right? That's good for you, right? Now look at here. I brought the other diagram. That's a chromium, right? Now read this. Let me ask. Let me ask the Abhishek Kumar. Abhishek Kumar, right? We have a limited time that I need to Abhishek, but still I want to. IE 10002. Abhishek Kumar, read the chromium lab cross diagram and tell me. Hadar Metha. Nobody listen. MA 20001. Metha. Anybody is there? No. Anup Singh. MI 31005. You are around? Okay. Answer. Anyone of you answer? This is too much.
CR3 plus is the most stable.
Yeah, a little louder. I'm not able to hear. Abhay Kumar.
CR3 plus is the most stable oxidizing state.
Okay.
CR207 2 minus is the
Dichromate is strong oxidizing.
Yes, very good. Dichromate. Cr2O7 2 minus K2Cr2O7. You should have used this in your laboratory classes. Okay. And then go a little bit here. The phosphorus frost diagram I have given. Phosphorus frost diagram I have given. You can draw from this looking at the diagram. The immediately look into the oxidizing agent, reducing agent. Where the species undergo disproportionation, the species will undergo comproportionation reaction. That you can read it from. You should read carefully, right? Yeah, I mean, don't worry that very small slope. There the question will be there. No, we won't do that. The visibly seen that will be asked, right? Okay. So H3PO2 and H3PO4, right? You can look at that. Possible reactions. pH3 and H3PO2, right? Okay. Again, I am bringing the manganese. Already I have explained already. Yeah, most stable oxidation state, right? Yeah, comproportionation reaction, right? Mn and MnO2 in acidic solution, right? Mn and MnO2, right? Mn and MnO2. Okay, but the rate of the reaction is hindered. In principle, Mn and MnO2 should undergo anybody. Comproportionation reaction, right? But the rate of the reaction will be experimentally. Experimentally, it may or may not go because of the insolubility of the rate of the reaction is hindered due to the insolubility. In basic solution, what we have MnO2 and MnOH twice, right? Already somebody mentioned this, right? MnO2 and MnOH twice, right? MnO2, no, nobody said, right here. Here you have. It will undergo this a facile reaction. Okay, right. So you should read very carefully looking at the diagram. Okay. Disproportionation reaction already we mentioned, right? We don't need to write. Overall, in the manganese, overall what we have from the frost diagram, thermodynamic stability is found at the bottom of the diagram. Mn2 is the most stable species. The species located at the convex curve can undergo disproportionation reaction. Already we explained. And any species located at the upper right side of the diagram will be a strong oxidizing agent, MnO4 minus and dichromate in the case of a chromium. Any species located on the upper left side, upper diagram will be a reducing agent. That manganese is a moderate reducing agent. Okay. Read that one. There's a delay. Yeah. Although it is thermodynamically favorable for permanganate ion to reduce to Mn2 plus ion, the reaction is slow except the presence of a catalyst. What is the reaction I'm talking about? I'm talking about MnO4. Already I have MnO4 minus to Mn2 plus, right? If you look at the potential, theoretically, it will undergo spontaneous reaction, right? MnO4 minus will get reduced to Mn2 plus, but it needs a catalyst. We call this potassium permanganate as a, anybody? Those who have studied, did the practicals. Potassium permanganate as a
Primary
anybody?
standard.
Primary standard. Very good. Yeah, primary standard or secondary standard? This primary secondary standard is not primary standard. That's what the point I want to make here. It is not the primary standard because it will undergo automatic decomposition. The K1O4 should be preserved in an amphor bottle or with a colored bottle, brown colored bottle, in order to prevent the decomposition of your K1O4. K1O4, right? K1O4 is a self-indicator, right? You know that. pH changes, pH and change in the pH may change in the relative stability of the species. I have already mentioned, right? I think there is no point of discussion. Now look at here, right? Please don't overlook, right? Don't leave the meeting, right? Sir has finished. That's why, I'm teaching the important part of the redox table. Okay, right? Look at the entire the first diagram of the first row transition elements, right? I want you to identify what is one species is odd man out. Who is that guy? Look at the diagram. Who is that odd man out? Anybody? Pardon?
Copper.
Copper, right? Copper, right? Unlike other species, the copper is. Yesterday I have mentioned this one. Copper 0 to copper 1 and copper 2 plus, right? So this guy is totally different guy, right? Completely different. Oh, you cannot use copper as a anybody. Copper as a
Oxidizing.
oxidizing agent. How? You
You
cannot
cannot
use.
use na.
All metals are good reducing agent. Read that. Exception is copper. How do I know that? The slope of the line is copper 2 to copper plus 1, right? Copper 0 to copper plus 1. The slope is completely different, right? From your rest of them, right? The reducing strength goes down smoothly from calcium to nickel. Nickel is a mild reducing agent. So you don't need to test, you don't need to get the potential. You look at this diagram, you will be able to see that entire first row transition metal or the first row D block element, you will be able to find it out. So early transition elements plus 3 state and later is that plus 2 state, the stable state. And iron and manganese, you have a multiple oxidation state, right? That is already we know that, right? The first row transition metal will have a multiple oxidation state, right? I hope you understand, right? There are species which is more powerful oxidizing agent than manganese, right? Here, this one species there, FeO4 2 minus or H2 FeO4, right? Is highly unstable, right? Those who study chemistry, you will explore this part, right? Okay, right. We'll come here. Group 6 transition metal. Right? I put we took a group, right? Chromium, molybdenum, and tungsten. Right now, you will be able to see that a peculiar characteristic of your chromium, right? With respect to the other members of the group, right? Completely different chemistry, right? So you will be able to read that. Yeah, chromium lies at the bottom. Dichromate, Cr2O7 lies at the upper right corner, right? You will be able to reduce the property. Another couple of diagram, then I will go to the battery, or I have some couple of diagram, and then I will go to the battery. Okay. So here what I have shown is indium, tellurium, and gallium and aluminium that I have shown here. And here is the sulfur group, oxygen, sulfur, selenium, tellurium. So you can, I am simply showing it. I am not going to read it again, which will undergo disproportionation reaction, which will undergo comproportion reaction. It's a mere repetition. So these are some representative examples of the Frost diagram. You should be able to read from here and answer the question, right? Another two diagram. and then I think I am done here in this. Then I will go to battery. Okay. Sulfur. Sulfur is one important, right? I will give some example the problems at the end of the class. Sulfur, you look at the different species. S2 minus, S8, S2O3, S2O4, H2SO3, and so on. Acidic and basic solution. Okay, right. I think I have done. I will bring the problem after finishing the battery part. I have the 4 or 5 slides problems are there. I will put it there. I will ask you to work out. Now what I should do is the battery. Okay. Now, so before going to the battery, once again, if you have what we have seen, particularly a Latimer diagram, LD, and then FD. That's a Frost diagram. Basically, the stability with respect to disproportionation reaction, comproportionation reaction, and the powerful oxidizing agents and reducing agents, all are based on the simple property of your E0. Whether it is a positive or negative, from there you will be able to simply deduce the property from the diagram, right? That's what we have seen in the another one is there, L-income diagram. So we are not going to that one. Let me go to the battery. Okay. Now, battery is a very important topic. Very important topic, but we don't have a time to go or look at the lithium-ion battery and all. I will explain briefly till nickel cadmium. Why we are in this is an application part of the redox chemistry that we are talking about. When I started the redox chemistry, I have mentioned where and all the redox reaction. I said that in biology, the multiple redox electron transfer, and then I said that in industry, that includes the extraction of elements, and also in the supercapacitor and battery. There it comes there. So the fundamental is basically a redox reaction. So what we'll do see here, a basics of primary and secondary batteries. I hope you know the primary and the rechargeable and not rechargeable batteries. Secondary is a rechargeable battery, primary is a not rechargeable battery. So that when we look at the electrical energy storage technology, there are multiple methods, right? This is very one hot area where people are constantly working on to develop a energy storage device. Due to several reasons, we are not going to explain this to that. A mechanical, electrochemical, chemical, electrical, and thermal. What we say, the pumped hydro or compressed air, flywheel, and electrochemical. There it comes your batteries and supercapacitor. Of course, we are not going to study about the supercapacitor. Briefly about the battery, we'll put few slides only. And in the case of a chemical, you have a hydrogen and the fuel cell, SNG. Electrical, you have a double layer capacitor, superconducting magnetic energy storage, and thermal, what we have the molten salt. These are the possible electrical energy storage technology that are available either in its a mature level or in the infant stage, right? Batteries are already developed, still people are working on that. Look at this diagram. Okay, yeah, there is a delay is there. Right, some funny pictures, right? It goes back, right? Goes back to 1800s. 1800, the birth of the battery, right? What the picture image that I have shown is Alessandro Volta, right? All of you should be knowing who is Volta. And then before that, somebody has done that. Louis Galvani, the galvanic cell, we remember, right? What he has done is an interesting story. He was working with the frog. Cut the frog, and then what he did is that he took the two different metals, a copper and zinc wires, and connect this portion and this portion. What he got is that we noticed that a twitching of the muscles, right? Twitching of the muscle, right? We cannot show the animation because this is a PDF file. Usually I used to show that I think last class I saw. This time there's a network issues there. So what happens? The frog legs are here. When it is not connected, when you connect it, immediately what happened? A twitching out. So what they called is that bimetal electricity, in other words, bioelectricity, right? Bioelectricity, that's what they mentioned. They did not bother anything about these two metal that is connecting. Galvani looked into said, you see, I am connecting the top portion and the bottom portion. So the frog itself carries some electrical energy. That is why when I connect it, it is undergo twitching. Your electrolyte is the fluid. There is a conduction, and then you are connecting your the two metal part. I mean, he did not notice that the two metal pot are two different. This basically is connecting the copper and zinc. Now you know that copper and zinc, if you put in a copper sulfate, zinc in a zinc sulfate, if you connect it, what will happen? Anybody? That's a
Potential
pardon?
development.
Yeah, right. You know that. Now, Volta came and refuted that. You see, that is not the case. What you are using is basically two different metal. The two different metal has a two different characteristic. This twitching or the potential that is generated is basically due to the some reaction in the metal. The fluids in the frog that function as an electrolyte, you are basically connecting two different metal. It is nothing to the bioelectricity. It is something to the bimetal. He refuted, and then he made this what we call the famously called the voltaic pipe. What he did, he took the cardboard, soaked in sodium chloride, he alternatively packed up one after another, and then measured that. And then later he said Volta's crown cup, he made in this way. There are plenty of stories there. Right? This is basically a modern zinc air cell, a crude form of a modern zinc air cell. Zinc air, right? I'm not sure whether you have come across that. Let's not go here. We'll stick to the copper and zinc. It's alternate zinc copper and a different the same electrolyte in a different the beaker, say for example. So basically what we have alternate voltaic pipe is connected and you get a potential, a beautiful illustration of the redox reaction between your copper 2 plus or with copper and zinc that is taking place, right? Now it doesn't stop there. It goes there. Daniel came. There are a lot of shortcomings here, right? This is a major breakthrough in electrochemistry. It's a major breakthrough. That the electricity generation. That what is the birth of the battery, right? Now we all of us play with the battery. Your gadget or your mobile or computer is powered by this battery. That is basic fundamental is here. Now Daniel came and he developed further modified primary cell with a ceramic spacer, right? Ceramic spacer, two fluid, right? Two different fluid, zinc sulfate, copper sulfate. You separated, right? What we call what we have is the instead of we call the saltbridge. Here you have a separator. The problem is that internal resistance due to the ceramic spacer and hydrogen bubble formation. That is inevitable, right? These two are the major bottleneck. Subsequent years, you may surprise that there are 37 variant of Daniel cell was developed during the year of maybe almost around 49 to 90, almost around 40 plus years, 40 plus women. And there are that include bird cell, Medinger cell, gravity, so many there. We are not going there. What I have shown here is that bird cell, right? The crowfoot cell. This is a crowfoot cell that I have shown that right hand side. I have marked it here. Right hand side, the crowfoot, this cell. Like this, many things happen, and also and then following it, Leclanche has developed. Instead of taking a zinc sulfate, in order to reduce the problem, get out of the problem, he used the ammonium chloride and MnO2, what we call the Leclanche cell. That is what we have: zinc, MnO2, ammonium chloride, zinc chloride. This is the one that in 1866, and then comes here. There's a major breakthrough in the primary battery. That is that Eucentro battery. That what we have, what we call the pencil battery, or what do you say that? Louis Frederick. It is an interesting story. He was basically working in Canada here with the Union Carbide. Union Carbide. That's a very famous industry. Eveready battery, that is a Union Carbide. He was asked to go to US to work on the battery. So he read the literature, collected the patent, all that. One day, after doing lot of work, you know what happened? Just that he called all the employees to the cafeteria of the company. He bought two toy car. The small kids play now toy car. Bought it. He developed a battery that is basically MnO2. Yeah, this reaction that what we have replace the ammonium chloride zinc solid with a KOH MnO2 zinc powder gel. And what is already available in the market? That is a one. There are two battery. One is he's developed, the one he developed, another one is a commercially what he bought. He ran the toy car inside the cafeteria. The what he bought in the shop, the car stopped within 30 minutes. Right? That means the battery's life is gone. But the battery could survive hours together. So that is a very major breakthrough in the primary battery development, what we call the father of alkaline battery. Father of alkaline battery is basically what we have your KOH MnO2 zinc powder gel. He renamed that conventional battery as an energizer because it energized the toy car. As a result, he put it. That is a very really groundbreaking story for that time. So redox reaction is not simply story. You should understand the redox chemistry there. Zinc oxide, MnO2, Mn2O3. The redox reaction. The corresponding potential is there. That is more important for your examination, right? At the end of the day, what it boils around is that what is more important, sir? What is important for the exam? That is more important, right? Usually, I don't tell. Right? Yeah, you look at here. These are the reactions that comes into picture. Now I will finish with the nickel cadmium, and then I will go to the problems that I have put in a couple of slides, and then if time permits, I have the videos to make you understand the redox reaction and other couple of these. There will be nickel cadmium. Right? This is Jugner, right, in 1899. Rather than the history, but you need to understand the chemistry behind the battery. That is more. The cell voltage is 1.2, close to the primary battery, but it's okay. How long it will survive, that matters. The schematic representation I have shown in the right hand side, you can see that how it is made up. The positive electrode reaction is basically nickel cadmium battery. That when we talk about the cadmium is basically a carcinogenic. Right, I hope you know. Carcinogenic. What does it mean? Anybody? Yeah, it causes cancer, right? Carcinogenic, right? But still, it is people. Most of the cameras and other use the nickel cadmium or nickel metal hydride battery. Nickel cadmium is still in use. Positive electrode reaction is what is happening here. Nickel oxyhydroxide, and it. Right, look at the arrow. What is happening during discharge? Right, discharge reaction is nickel oxyhydroxide to nickel hydroxide. Okay. On the other hand, charging reaction is nickel hydroxide to nickel oxyhydroxide. So this is basically your secondary battery, rechargeable battery, nickel cadmium. The negative electrode is, right, we say the nickel cadmium, right? Positive electrode is nickel. Basically, what is happening? Nickel oxyhydroxide that is generated on the surface undergo the reaction during the charge discharge. The negative electrode reaction is cadmium. During discharge, what is happening? Your cadmium get converted to cadmium hydroxide. And during charge, again it comes back with the potential of minus 0.8. Here it is your 0.52. The overall cell voltage turn out to be only 1.2 volt. Right. Overall battery reaction is, look at here. Battery reaction. Nickel oxyhydroxide, cadmium. What we have? Nickel hydroxide, cadmium hydroxide 1.32. Theoretically, cell voltage will come only 1.2. Now, look at that. Carefully look at this equation. The two reactions, right? Carefully look at the two reactions. the positive electrode reaction and negative electrode reaction. Right? Can you tell me what is so specific here? Anybody notice? Anybody? I will explain you, right?
Sir, pH not involved means you are
Pardon?
not, pH is not involved at any pH. This will be.
pH is not involved. You should go a little more, read little more of. The main problem in the lead acid the battery, the conventional lead acid the battery is a flooding. Right? You generate water, the volume increases, and then goes up here. Here, carefully look at the nickel oxide hydroxide. For the positive electrode reaction, you are generating OH minus. Okay, that is being consumed in the at the negative. Right? I hope you are following. At the end of the day, what we have, right? Nickel oxide hydroxide, cadmium, water. You'll come here. It will be there is no volume expansion, typically, theoretically, ideally, right? It may go beyond, right? That's not in our control, right? When you overcharge or some other experimental condition, if you change it, that will happen. Here, basically, I generate the OH minus in the positive at the positive electrode, which is being consumed at the negative electrode. So there, in principle, there should not be any volume expansion. That is so unique, right? Because whatever I generate, I to consume in the next electrode, as a result, it should be intact. It's not always easy to do that. Carefully look at the equation, water molecules, right? That's what, right? Concern is cadmium is a pair. Oxygen generation of the cathode upon charge is one of the issue, right? Oxygen generation, oxygen, what we call the oxygen evolution reaction. Oxygen evolution. When it go beyond the cell voltage, overcharge, there is one issue. Typically, ideally, it doesn't go, right? When you overcharge, that's the one reaction. That look at here, what is actually chemistry? You have your nickel oxide hydroxide. I put in a square scheme. Discharging, you are getting a beta nickel hydroxide. Here I simply mention nickel hydroxide. Actually, what is that? A beta nickel hydroxide. Now, when you overcharge, look at the equation very carefully. When you overcharge, what you are getting is basically you are generating other phase, right? Right, gamma. These are the different crystal phase, right? We don't have time to teach the material chemistry. Otherwise, we'll be able to address the phases. Alpha, beta, gamma. Different phases, different crystal structures. So when you overcharge, what you get is a gamma nickel hydroxide. That is the byproduct. The side reaction that takes place, you are getting this one. And then one beauty is that this can be converted into nickel hydroxide. Either by this way, say for example, you discharge it and then you get your alpha nickel hydroxide, and then when you age it, you may get into a alpha nickel hydroxide, which is initially needed for the charge discharge reaction. You may ask that, sir, doesn't this will also reaction? Yes, this can also. That is a gamma nickel hydroxide, oxyhydroxide, and alpha nickel hydroxide can also undergo charge discharge. But primary cell reaction is this one. This is the basically a cell. So if you are overcharging, you are generating something else that undergo alpha nickel hydroxide. This basically what you are doing is that the lifetime of your battery is going back. I mean, it's very less with respect to the ideal. Ideal one is, you restrict to this, the first reaction. That one. Right, the crystal structure I have given here, alpha beta nickel hydroxide and then beta nickel oxyhydroxide. What's the crystal structure? Don't much bother. But you should know that what is the redox reaction that is taking place. Nickel oxyhydroxide to nickel hydroxide, overcharge, you're getting your gamma. Then that also can be converted during discharge to alpha. While aging, you get your beta nickel hydroxide, which is the primary. Right. Now, silent features, right. I will not go to the next story. Don't worry. Right. Outstanding economy and long service life, which can exceed up to the 500 charge discharge cycle. That's one beauty. Okay. The beauty of is the 500 charge discharge cycle. Low internal resistance, which enables a high rate of discharge, and a constant discharge voltage. That is, the internal resistance is less. I mean, low. Completely sealed construction, which leakage will not be there, but the leakage is completely sealed. So electrolyte leakage is, yeah, I mean, you don't need to bother. It's a maintenance free. One good thing is that, look at here, even if you overcharge, what you can get back, though you lose a little bit of the capacity or the power, but you will be able to get back. It's not an irreversible loss. Because when I overcharge, I get a gamma nickel oxyhydroxide, which on discharging, you will get your alpha, which can be converted into nickel oxyhydroxide without any issue, right? Within the cell itself, that's one beauty. Though it is a side reaction, but you can recycle within the battery. That's one of that. Ability to withstand overcharge and over discharge. That is one. Right, long storage life without deterioration of the performance. There's among the batteries, there's nickel cadmium is one of the, I mean, the best battery for portable electronics of smaller scale. Right, wide operating temperature. That's another one. We will not be going to study the temperature effect and all. So that's all about your redox. I have explained you in the battery. What I have explained is that one primary battery, that is basically a alkaline battery of Lewis, and another one is the secondary battery, that is nickel cadmium battery. So what you need to understand is the redox reaction involved, what are the electrolytes, what is the cell potential, and so on. That's all about the batteries. We have many more that usually I used to teach all this, the lead acid, and then finally end up with the noble orange, right? This, you know, the noble orange, right? The lithium ion battery. So we are not going to, this time we decided not to, dump everything on you. We limited the syllabus to make your study life little ease, right? Okay. Now what I will do is that I will go to the redox. I will show you. I'm not going to do anything. Look at this. The slide. What I have done is that what I have given the three, number 1, number 2, number 3. Okay, 3 Latimer diagram I have given. Okay, now you yourself answer the question that I have written at the bottom. Okay, what I have that, what is the reaction of MnO4 minus with 5 equivalent of VO2 plus. Look for the species in the any of the Latimer diagram and find out. These are the model questions that usually how the questions will be asked. That so what is the reaction of MnO4 minus with 5 equivalents of VO2 plus, right? When you talk about the VO2 plus, look at that carefully. 2 plus is the oxidation state, right? Yeah, have a look at and then answer.